Hi, I'm Dr. Jason J. Campbell, and I want to thank you for taking the time to watch my videos. In this video, I'm going to actually do a response to a comment that I got on, I think it was video 8 of my introduction to predicate logic. Gramo83 said, "Hey, Dr. Campbell, you forgot to do indirect proof," and he's absolutely right. I thought, or she, Gramo83 is absolutely right. I went through universal instantiation, universal generalization, existential instantiation, existential generalization, conditional proof. I forgot to do indirect proof. So I'm going to sort of tidy up my analysis of predicate logic by demonstrating an indirect proof. Gramo83 also asked if I could give an example of an indirect proof that also had a conditional proof built into it. So what I did is I created a problem that has both an indirect proof and a conditional proof built into it. And this will serve as an example, and this will conclude basically the series in predicate logic. My apologies for overlooking that. Gramo83, thank you for the heads up. And here is the answer to your question. So this is going to be formal proofs of validity within predicate logic. Alright, so this is formal proofs of validity within predicate logic, and we're going to do an indirect proof and a conditional proof in this example. Okay, so let's first write out the problem. That's too big. For all x of x. And then 1, 2. Oh, not that. Oh, for all not jx and kx. Fx or rx. Not Alright, let me just check to make sure I did that right. Boom, 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 boom. Then not g, x, and kx. Therefore, okay, so the problem is symbolized correctly. So in response to Gramo83's question, this example will serve as an example within predicate logic that uses both indirect proof and conditional proof within the same problem. Before I get into the actual proof, though, there are a few things that I want to address, namely the following, right? And this is sort of an analysis of how this works, right? When we're talking about, when we're talking about conditional proof, this is how, and I've already done a video on conditional proof, so I'm not going to get, the last video, video 8, was on conditional proof, but just to sort of set the stage, in conditional proof, what we're given, right, is a conditional statement, if P then Q. What we want to do is we assume P, right, in a line assumption, and then what we attempt to do is we try to derive Q. Right? We try to derive Q. After we've derived Q from the assumption P, then we recognize that this is valid, so then we write if P, then Q from line 1 to line N, right? And this would be line 1 through N, and the justification is conditional proof. Right? So that's how that's written, right? And just so that this is highlighted, the justification is line 1 through N, conditional proof. Okay. When we attempt to do an indirect proof, there's a structure for how indirect proof is solved. And the whole point of me giving this example, one, is because I forgot to do an indirect proof. Two, because Gramo 83 asked for it. But three, also, it's important to recognize the theory behind it, because knowing this theory will help formalize your argument, right? There's a certain way that you should set your argument up. Obviously, I'm going to teach you the way that I find best. There are many different ways to construct your argument, but for me, this is the easiest way. All right, so when we're talking about indirect proof, we are going to be given a conclusion, and we'll just say that conclusion is n, whatever n is, right? For an indirect proof, what you want to do is you want to assume the negation of this conclusion, right? So it would be not n. And if you were given not n, you would assume n, vice versa. Whatever you're given, you're going to assume the negation of that thing, whatever that thing might be, right? So again, this is sort of like the theoretical understanding. In your premises, you'll be given as a conclusion n. You're going to assume the negation of n. What you're attempting to do is you're attempting to derive a contradiction, a and not a, for example, right? Once you've derived, this is line 1, this is line n. Once you've derived a contradiction from the negated assumption, you draw a line that goes up, arrow goes here, and you reaffirm now the original conclusion, right? You reaffirm the original conclusion. Why do you reaffirm the original conclusion? Because the negation of this conclusion led to a contradiction. So we would put whatever n is down here, reaffirm n now. We're not using not n anymore because that led to a contradiction. We reaffirm n, right? And the justification for this is line 1 through n, indirect proof, right? So, step 1, reaffirm the negated conclusion. Step 2, arrive at a contradiction. Step 3, reaffirm the original conclusion. And the justification is going to be the line the assumption starts on, for this example, 1, the line the contradiction is derived, right? So 1 is the assumption line. N, wherever n might be, is the contradiction line. And then obviously the justification, right? So 1, whatever that line be, if it was line 4, whatever line you made the negated conclusion assumption, that's this line. Whatever line you arrived at the contradiction, that's the range, the scope of it, and the justification is IP. Now, I've given you an example of a conditional proof, but what Gramo 83 asked for was for an example that had both a conditional proof and an indirect proof built into the same question. So what I did was I went through and I created the following 2 premises and this conclusion, because I know that I'll have to use both. As a quick aside, it's important to recognize if you want to increase your proficiency in symbolic, modal, predicate logic, whatever logic it might be, it's a really good practice to create examples for yourself, right? If you can create an example for yourself and check the validity of the argument and find out that the argument is valid and then solve it yourself, you really increase your expertise in this ability. The one thing I have to say is that what I'm going to show you today is the traditional method, right? It's the method that most people are familiar, 99% of logicians are familiar with the type of solution that I'm going to give you. Obviously, an indirect proof is nothing more than a reductio. However, I personally use a different format for reductio, a much easier format for reductio. I'm not going to go into it because I've already done a 4 or 5 part series on sort of my version of solving reductio. You can solve reductio and check validity using the indirect proof, which I'm going to show you today, or you can do it in the manner that I showed in the 1 through, it's like solving problems using reductio ad absurdum videos 1 through 5 or something like that. It's an alternative method. I think a much easier method of assessing validity, but the question that I got from Gramo 83, and thank you for the question by the way, was the use of indirect and conditional proof. So I'm going to show you the traditional model of solving these problems. So I think that covers all my bases. So now we can begin our solution. Here we go. Alright, so for for me, the way that I go about solving these problems, there are many different ways, but the first thing that I do is I always put my assumptions first, right? So we recognize that there are going to have to be two assumptions in this solution, and the question is, well, why are there two assumptions? Because the question was to have a conditional proof and an indirect proof in the same problem. So line 3 and line 4, this is going to be a long problem, so I don't want to make it too big. Line 3 and line 4 are going to be my assumptions. Okay. Another sort of bit of theory. Anytime we are making an assumption based on conditional proof, the conditional proof has the format of obviously a conditional statement, an if-then statement. What we're going to do in our conditional proofs, and you know this because I've already said it, so I'm not going to go into too much, is that we assume our antecedent, right? And we attempt to derive our conclusion, our consequence, from that assumed antecedent. This is exactly what we're going to do in this statement, right? Also, we recognize that the second thing that we need to do is we need to, for the indirect proof, we need to derive, as we said, a contradiction from the negated assumption, right? So we recognize that we have to have a negated assumption. So we're going to have two proofs, or two assumptions rather. First, we're going to assume our antecedent, right? So we have Fy or Iy. Oh, and I had a question. I forget who was asking me the question. I went through a good back and forth with a viewer as to why I instantiate with y. And I forgot to sort of mention this, so I'll do a quick, I don't want to go off too far on a tangent. So, for example, if we have Socrates is a man, right? So the predicate is man, the subject is Socrates. We recognize that we instantiate Socrates as a man like that. However, we can also, well, and the reason is, well, why do we instantiate Socrates as a man like that? Because we recognize that within the scope of all things man, that Socrates is one instantiation of the concept man. He is an instantiation of the concept man. But he's a very specific instantiation of the concept man. Since the way I solve my logic problems is I don't, I'm not going to present you with a paragraph, because logicians never find this in the real world, right? You're never presented with a paragraph, and you're going to have to translate the paragraph into its symbolization and then deduce your validity, or prove your validity, or deduce your conclusion. What I do is I just instantiate with any general random instantiation, and y is used for that. So instantiating with S, right, A through W is a specific instantiation, right, of whatever your predicate term is. If you instantiate with y, then what you're saying is, given the scope man, right, don't instantiate with a specific man, instantiate with any general man at all, any man that you want, and that instantiation is represented by y. So y is a representation of any arbitrary selected instantiation within the set of all things man, to be technical. And since my problems aren't based on words, it's just the logic, because it's good for instruction, I always use y as my instantiation. So hopefully that clarifies that. Okay. So what I've done here, as you've seen, is that I've made my assumption, right? Fy or Iy, and to be technical, this is saying for all x is an f, or x, if x is an f, or x is a y, then it is not the case that x is an h or x is a j, right? So that's what we're attempting to do. So the first thing that I did is I made my assumption for my conditional statement. You should know immediately that since we've made this assumption, that we need to derive this conclusion this consequence rather, in order to tidy up this initial assumption. So we're looking for this somewhere in our problem in order to tidy up this first assumption. So this is assumption, right? And if you're just getting, just being introduced to predicate logic, what I did when I first started, and this is good practice, it's not proper sort of syntactically, but it's good practice, is I always put what I'm doing here. What is this assumption, right? So I put, for me, I would put, CP. this is a conditional proof that I'm trying to get to, right? Technically, you should not have this in your solution, but it's good for visual, right? It's like, oh, that's right. On line 3, I made a conditional proof assumption, right? The assumption that I made was a conditional proof. Syntactically, it's not proper, but, you know, it doesn't really matter. This is the ghetto version. Alright, so that's my assumption for my conditional proof. My next assumption is going to be my indirect proof. And my indirect proof assumptions, an indirect proof is always going to be concluded, right? The conclusion of an indirect proof is always going to be a conjunction, always. The conclusion of a conditional proof is always going to be your conditional statement, right? So if you see a conditional statement at the end of the solution, you recognize that it tidies up, if you've done your deductions properly, it tidies up your conditional proof. When you see, and obviously your conjunction is going to be a contradiction, so the conjunction of two contradictory claims will tidy up your indirect proof, right? So what did we say in our formula, right? We're going to assume the negated consequence, right? The negated consequence. So here's the consequence. Not x is an h and x is a j, right? Not x is an h and x is a j. The negated consequence of that is going to be h, y, and j, y. Obviously, again, we've instantiated to y, right? We've instantiated to y. There isn't a problem because we're talking about universal generalizations, right? So no problem there. All right, and this is an assumption as well. And this is, what is this? This is indirect proof, right? Again, syntactically not proper, but it's good to know. The next thing that you should recognize, so sort of our problem is starting to build slowly, right? We're starting to answer this problem slowly. The next sort of theoretical point that you should be made aware of is that if we are talking about a problem in which we have both a conditional proof and an indirect proof, we recognize that in this specific problem, you should see that our indirect proof is going to have to be within the scope of our conditional proof. So we'll have the scope of our conditional proof, and within that scope will be our indirect proof, right? Our indirect proof will be held within the scope of our conditional proof. It's not going to be the other way around, and that's important, right? The conditional proof will have a larger scope and contain the scope of the indirect proof, and we'll see, I'll prove this in a second. Okay. The next thing we have to do, and there's a lot of steps into this, in this problem, and I completely see why Grandma 83 asked the question. It's a very good question to ask, and again, I probably should have recognized that I didn't do an indirect proof, but you know, now I'm doing it. Better late than never, is the saying. Next thing that we want to do is we recognize that all of our assumptions have been made, right? We've assumed our antecedent here and instantiated it, and we need to prove our conclusion, which is not x is an h and x is a j. We've assumed our consequence, and we need to derive a contradiction. Once we do that, we'll have tidied that up. But we also have two generalized terms that we need to instantiate, and that shouldn't be a problem because I've already given you a lecture on how to instantiate universally, right? This was on, I forget which video it was, but it's one of the predicate logic videos where we talk about universal instantiation. So we're just going to do a regular universal instantiation for both 1 and 2. So line 5 is going to be the universal instantiation of this claim, and this claim specifically is for all x, if x is an f or x is a g, then x is not an h, right? So let's instantiate that. We get fy or gy. If fy or gy, then not hy, right? And that's going to be universal instantiation of line 1. So that's line 1, ui. Okay, so we have our assumptions done, our first instantiation, and now our second instantiation. Line 6 is going to be I, y. If iy, then not jy and ky. And that's going to be line 2, universal instantiation as well. Okay. Our two assumptions, our two instantiations, let me make sure I just did that right. All right. Hy, IY, JY, KY. Okay, so we've instantiated all of our claims. Our next line, line 7. Let's see what we can reduce a bit. We see that we have a conjunction here. This conjunction can allow us to get this HY, right? So we can get HY, or Y is an H, from a simplification on line 4. So that's line 4 simp. So we get HY from simplifying line 4. What I would do is I'd just go ahead and try and get the JY as well. Why not try and get it now? So on line 8, alright, let's do commutation. So we get JY and HY, and that would be line 4 commutation. Okay, so we've done commutation, and as far as commutation, you guys know, right? HY and JY is exactly the same as JY and HY. We've done commutation on that. We need this, in order to get the JY by itself, we need it in the position of P and Q, and then we simplify, right? So line 9, we can now get JY, and that is simp on line 8, so that's line 8. Okay, so we've isolated HY, we've isolated JY. Okay, what can we do with that? Okay, we see that we have not HY here and HY here. These are indications, right? The way I like solving problems is I like to isolate my terms. If this is just my particular style. If I isolate my terms, then I can better see where I can manipulate my terms, right? Where I can do modus tollens, modus ponens, where I can do sort of addition or disjunctive syllogism or what have you, right? So if P then Q, right? If P then Q, not Q, the opposite of it, not Q, therefore not P, right? So if I eat too much, my stomach will hurt. If I eat too much, my stomach will hurt. My stomach doesn't hurt. Therefore, I haven't eaten too much, right? The negation of my antecedent. So number 10 is going to be not Fy or Gy, and the justification is line 5 and line 7. What is that? Modus tollens. All right. So we use 5 and 7 modus tollens to get this claim, right? Once we see this claim, then we recognize that you know, you need a little bit of practice to be able to see this, but you recognize that we can change this disjunct into a conjunct. And the way you change the disjunct into a conjunct is by using De Morgan's, right? And there's only a few rules, most of which are very, very small. To get into practice, what I did for the first year or so is I wrote the rules of inference, and I've provided you with the rules of inference, and I'll also give you a link to the rules of inference from this video. I have to remember to do that. Just getting the practice of writing the rules of inference down on a cue card, and then, you know, drilling yourself so that until you get it. But you can transform this disjunct into a conjunct. And the way that we do that is through De Morgan's. So number 11 is going to be not Fy and not Gy. Right? We've distributed the conjunct, and it transforms the disjunct into a we've distributed, the negation, and it transforms the disjunct into a conjunct. So we have not Fy and not Gy, and that's De Morgan's on 10. So that's 10 DEM. Okay, that's good. What do we need now? Fy. Okay, so here's Fy and here's Fy, right? So we know we can get Iy, right? Because if we're, oh, well, no, first I need to isolate, sorry. 12, let's isolate this Fy by simplification, so we get not Fy, and that would be 11 simp. So on line 11 we did simplification, and we got Fy. Now that we have Fy isolated, we look through all the problems, and that's what I was doing. I was looking to see where I can see another Fy. Don't see any. I see an Fy here, right? We recognize that we can do disjunctive syllogism on line 3 and line 12, right? Fy or Iy, not Fy. Therefore, it has to be Iy, right? So on line 13, we can get Iy, and the justification is line 3 and line 12 DS, right? 3 and 12 disjunctive syllogism, right? Okay. What else? What else? So we got IY isolated. Okay, IY is here, IY is here. If P, then Q. If P, then Q. P, therefore Q. Right, so we can get this. Right? So 14 will be, what is that? Not JY, and KY. And that's modus ponens. If P, then Q. P, therefore Q. So, and that's if I jump, I will fall. If I jump, I will fall. I jump, therefore I fall. Therefore I fall. Right? So that's MP on 6 and 13. 6, 13 MP. Okay, now we see that we can finish this up, right? We have a JY here, and I'm about to get a not JY here. Once I get this not JY, this is going to conclude my second assumption, right? Because I've derived the contradiction. So on line 15, we're going to do a, no, first we have to do simplification here. So then we get not JY, which is line 14 simp. Line 14 simp. Okay. Now we can do a conjunction between line 15 and line 9. So 16 is not JY and JY, which is, what is that? That's line 9 and line 15, CO and J. Okay, so we've done line 9 and line 15, JY, not JY, conjoined them. I've arrived at my contradiction. Remember, as we said before, the whole point is we make an assumption of the negated conclusion, right? We make an assumption of its negation. Here's our consequence, here's the negated consequence, right? From this assumption, we were able to derive, just like here, we were able to derive a contradiction. Here's our contradiction. We tidy it up now, and I'll do a different color. We tidy this up by right? This is our indirect proof, right? Our indirect proof, and this is why it's important. This is why I do this, right? You can erase it after you've done your solution, but you don't want your arrow to go to the wrong thing because then your scope will be off. If you put it here, your scope's wrong. Your scope begins here, your scope ends here for the indirect proof, right? So then we do our justification. Excuse me. Do our justification on line 17. So line 17 now, we've recognized that we've done our justification. What goes here, right? Again, the formula tells me that if I assume the negated conclusion and derive a contradiction, then what I have to do is reaffirm the original conclusion in my line. So the original conclusion is here, right? The original conclusion is here. Obviously, it's generalized. We can't instantiate it generalized. We have to instantiate it as an instantiation. So it's going to be HY, oh, not HY, sorry. Not HY and JY, right? You can't, because it's instantiated claim. It couldn't be X, right? It couldn't be X. So remember, what were we trying to prove? If we make this assumption, we're trying to get to this conclusion. We are able to do that, and the justification is line 4 through line 16. So it's line 4 through 16, indirect proof. So this tidies up our indirect proof. What we recognize, however, is in tidying up our indirect proof, our initial assumption for our conditional proof has now been resolved. We assumed that we're going to have this instantiation, right? And we're trying to derive this conclusion. We were able, from our initial assumption, to derive the consequence, the instantiated consequence, to be technical. So this concludes our, line 17 concludes our initial assumption, right, for our conditional proof. So we can tidy that up, right? I keep on driving this thing. Let me just out the way. Okay, so that tidies this up. So we go here, go back up to line 3, and this is what I was saying. The scope of my conditional proof contains my indirect proof. My indirect proof is within, that's why I said it was like this, CP, IP. That's why I made that graph before, because the indirect proof is contained, 4 and 16 is contained within the scope of 3 and 17, right? So what we do now, and you know, it is a pretty bestial problem, but hopefully it's not that complicated now. You sort of see how to progress through it. What we need to do now in line 18 is make our conditional statement. Remember, we've arrived at our conjunction, which was a contradiction. This concluded our our second assumption. The next thing that we need is we need to arrive at a conditional statement, right? And that conditional statement is going to be of the form this here. It's going to be our original antecedent, which is Fy or Iy. If Fy or Iy, then what? Well, then 17, right? So it would be not Hy and Jy, right? And that's going to be justified by lines 3 through 17, conditional proof, right? Lines 3, where I made my initial assumption, to the consequence I was trying to derive, and that's going to be conditional proof. So that's going to be 3 through 17, comma, conditional proof, right? So now, as you can see, the question that Gramo 83 asked, which was very technical, it's important to recognize how you progress through this, right? If you make your assumptions in the wrong order, that can mess it up. If you don't instantiate properly, that can mess it up. But as we see, it's really not that complicated. The majority of this problem is just regular deductions. The only thing that you have to be careful for, to be honest with you, is really just your assumptions. And it's really not that hard if you lay it out slowly, sort of methodically. So we see that this has the form that this has, right? This is the identical instantiated form of this. So all we need to do to attain this conclusion, because this is what we're trying to get, here's our conclusion. All we need to do to attain this conclusion is to universally generalize, right? Fy, Fx, or Iy, Ix, then, not, Hy, Hx, and Jy, Jx. So all we need to do is universally generalize, and we've solved our problem. So step number 19, and I gotta get a little low here, is going to be for all x, Fx, or Ix, then not Hx and Jx. And the justification is going to be line 18, universal generalization. And that concludes the problem. Alright, so it's important to recognize that you can use conditional proof with an indirect proof. The most important thing is understanding sort of the theory, to be honest with you, is the hardest, is not even hard, I won't say it's hard, but it's the most important thing, right? Conditional proof, we assume the antecedent, important, we assume the antecedent, we try to deduce the consequence, right? You assume the antecedent, deduce the consequence. We assume the antecedent, here's the antecedent, assume the antecedent, and we want to deduce the consequence. We're able to deduce the consequence, right? Assume the antecedent, deduce the consequence, okay? So that's how they that up. In an indirect proof, you assume the negated conclusion, and then we derive the contradiction. Assumption from the negated conclusion, derive the contradiction, and then that tidies that up. And then the rest is just sort of, you know, general, universal generalization of your initial instantiated claim. So hopefully that that helps. I want to thank Gramo 83 for reminding me that I hadn't given you this example. With this example, it tidies up all of the analysis of predicate logic. There are more things that I can do in predicate logic, but with what you have now, you should have, you know, with a 9-part series, you should have enough in order to be able to solve any problem, for the most part, within predicate logic. So, again, I want to thank Gramo 83, and I want to thank the general viewer for taking the time to watch this analysis in this formal proof of validity within predicate logic for conditional proofs and indirect proofs. With that being said, I'm Dr. Jason J. Campbell. Have a good day.